And thank you everybody else for staying all the way till the last session. Again, my name is Brendan Saltaformaggio, and I'm a PhD candidate at Purdue University. And today I'm going to be talking about my newest memory forensics technique called RetroScope. RetroScope enables the spatial-temporal reconstruction of a previous screens that an Android app was displaying based only on an input memory image. But first, this is a forensics talk, and I think that any forensics talk must begin with a crime that we're here to investigate. So imagine before the investigation begins, we're watching the suspect interact with their applications. In this case, using the Telegram app to message one of their contacts. Maybe setting up some kind of illegal deal because he's telling them, let's meet tonight. But before the suspect sends off this message, he hears the police coming to the door and panics, quickly logging out of the Telegram app, and now the suspect thinks that he's safe. Because, as some of you probably know, Telegram is a very secure app, especially once you've already logged out. So the police are going to arrive, they'll confiscate that device, image its memory, and we're going to see how RetroScope is going to reconstruct the previous screens we just saw the suspect using. But I'm going to go a step further and say that RetroScope is going to do this without access to the suspect's password and without breaking Telegram's fully encrypted storage. So like I said, this is memory forensics. And the goal here is to recover all of that evidence that we just saw on the suspect's screens from an input memory image. However, this may be mission impossible. Some of you might remember my paper Guitar, which got the best paper at CCS last year. But Guitar was only able to recover the most recent screen that an application was displaying by geometrically piecing back together all of the remaining GUI data structures in a memory image. And because of that, Guitar comes with a very serious limitation. For every new screen that an application displays, it's going to overwrite and destroy the GUI data structures from the previous screens. So no matter how many screens an app displays, Guitar will always be limited to only the most recent one. If we number these screens backwards in time, then we can say that Guitar is limited to only screen 0 and none of the previous. And what's even worse, if the suspect has already logged out, like we just saw in that video, then that screen 0 is going to be of no use to investigators. But I know what you're thinking. Are those old screens really gone? When I use my Android apps, the screen changes are highly dynamic. If all that GUI data is gone, then how can every screen be rebuilt so quickly? Some data must remain to allow the applications to bring those old screens back. Well, we're all scientists here, so we did some experiments to answer those questions. We profiled the app's memory usage, so you can see that the x-axis here is time and the y-axis is data structures that remain. And we found that the application's GUI data gets allocated and lost with each change of the screen. Now, these are the Android framework's generic data structures that every application uses that are ready to be rendered on the device's screen. And this is exactly why Guitar is limited to only screen 0, because Guitar can't recover the GUI data that no longer exists. But we also found that an application's internal data accumulates during the app's use. This is all of that raw data that an application generates internally, things like chat strings or account balances, that if an investigator wanted to understand, they would have to perform application-specific reverse engineering on each of these apps. So to answer that question, are the old screens really gone? Well, yes and no. Yes, the screens themselves are totally gone from memory. But also no, because the app's internal data that used to be shown on those screens does remain. And so that got us wondering, how does Android handle transitions in screens? Well, it turns out that Android just asks the application. Android sends a redraw command to a running app and provides it a blank canvas to draw its screen into. The application's customized drawing routines then execute and package up all of that internal data to fill up the canvas. It's this operation that destroys and overwrites all of that previous screen's GUI data. And then once the app's custom drawing routines are finished, that newly filled canvas can be rendered on the device's screen. It's this redraw mechanism that allows the Android framework to bring up any of the app screens that it needs without interacting directly with that internal data that it can't understand. Sort of like when you turn on your car using the key versus hacking directly into the engine. But this gave us an idea. Why don't we ask the app that's in a memory image to redraw its screen? I know, sounds a little crazy. First off, how do you even inject a redraw command into a memory image? It's just a blob of data, right? Second, do we need to understand all of that application internal data in order to do this? I hope not, because we want an application-agnostic solution, something that will allow investigators to plug in a memory image and get results out for any application that they're investigating. And then even if we did solve those two problems, a memory image is still just static data. So how can we get that new GUI screen rendered outside of the memory image for investigators to take a look at? But that's exactly what RetroScope is going to do. See, RetroScope acts sort of like a puppeteer, steering the live Android GUI drawing code towards that memory image and all of the app's internal data that it holds. This allows RetroScope to perform app-agnostic screen recovery for as many of the previous screens from that app that the memory image can support. And now I'm going to go through how this technique works in detail. So first, the Symbiont App. The Symbiont App is just a minimal Android application with its own runtime environment and GUI that executes all by itself. But this Symbiont App is going to serve as a host for the memory image app's redrawing. So RetroScope is going to move all of the state from the memory image app into the Symbiont App. This requires remapping all of the memory segments, merging the two Java runtime environments together, and bringing back all of the old code that the memory image app was using. So at this point, the Symbiont app is essentially two apps in one, but neither of those apps knows how to communicate with each other. To take care of that, we use our novel Interleaved Re-Execution Engine, or IRE for short. Now, this figure may look pretty complex, but this is actually a simplified version of an even more complex state transition diagram in the paper. Basically, we've formally modeled the interleaving of these two executions as a finite automata, with state transition rules based on each executing instruction's semantics. If you're interested in all the different state transition rules, then please see the paper, because it's actually a pretty fascinating technique. But if I were to really oversimplify this, the IRE is going to make sure that the live code outputs to the live GUI environment, and the old code is going to read from that old internal data that's in the memory image. Now I'm going to go through a quick example to show you exactly how the IRE allows us to redraw those screens from within the Symbiont application. So first, RetroScope starts just like the Android framework does, sending a redraw command to the Symbiont app and giving it a blank canvas to draw into. But instead of executing the Symbiont app's drawing routines, the IRE is going to be monitoring the state transitions and correct the execution into the memory image app's drawing routines. And you can follow along. I'm going to highlight the state transitions we go through on the side here. At this point, the memory image app's drawing routines are going to execute naturally and handle all of that internal data that only they know how to. And this is going to cause all of that previously lost GUI data to be rebuilt from the internal data in the memory image. Finally, the drawing routines are going to begin to fill that canvas. But the IRE is going to realize that the canvas is not from the memory image. It comes from the live GUI environment. And so it's going to correct that execution back into the live GUI environment to fill up the canvas with the GUI data. And you can kind of see on this automata that these mixed execution states are where things begin to get tricky, because the IRE needs to make sure that the old code interacts properly with objects from the live execution environment. And then finally, once the canvas is filled, it's already in the live environment, and so it can be rendered naturally by Android. And then the newly rendered screen can be saved for investigators to take a look at. And then RetroScope is going to reset and repeat this process for every drawing routine that the memory image app had previously registered. So remember that case we started off with at the beginning of this talk? Now we're going to watch how RetroScope is going to break that case wide open. So RetroScope runs in this modified Android emulator, and we're going to watch RetroScope's progress in the terminal. The investigator just needs to start the Symbiont app running inside of the emulator. And once that loads up, it's going to begin pulling in the memory image and merging all of that state to prepare the memory for interleaved re-execution. This process is going to take about 3 minutes, but thanks to the magic of Hollywood, we're not going to have to wait that long, and we'll skip right past that and get to the re-execution piece. Okay, so once everything is prepared for re-execution, RetroScope's going to begin reanimating those drawing routines. So remember that state transition diagram we just saw? This is RetroScope logging each of the state transitions that it goes through while it's reanimating. So you can see that it requires quite a few state transitions just to reanimate a single drawing function. It took 2 minutes to reanimate all of the drawing functions that were in this memory image. And then once this is finished, RetroScope will close to tell investigators that the results are ready. Okay, so RetroScope is done, and investigators can take a look at the results. To do this, we just have to pull them down from the emulator where they've been saved. This will take a quick second, and then we'll be able to look at them on the local computer. Okay, so in this case, RetroScope recovered 6 screens out of that memory image. We're going to go ahead and take a look at them, starting with screen 0, right? That's the most recent screen that the suspect was looking at. And for comparison, I'm going to rewind the suspect's activities that we saw at the beginning of this talk. So of course we recover the login screen as screen 0 because we saw the suspect previously log out at the end of his use. And investigators know the suspect tried to log out because we actually recover the logout dialog as screen -1. Before that, the suspect had logged out from the profile screen, so that's what's recovered as screen -2. And then we did that from the recent chats screen, so that's what's recovered as screen -3. Now this is interesting. The chat screen is still recovered with the draft intact, because of course that's how it looked the last time that the suspect had it up on the device's screen, and so it's still in memory, and that's what RetroScope recovers for screen -4. And then of course the first screen we started off on was the contacts list screen, so that's recovered as screen -5. So that's the 6 screens that RetroScope recovered from that memory image. And if you're interested, RetroScope is publicly available. There's a link there. There's a link in the paper. There's also a link on my webpage. But what I'm working on right now, and it's going to be up probably by the end of the week, is what I call RetroScope in a box. It's a pre-configured VM with RetroScope in it and some test case memory images that you can download and play around with on your own. I'm going to have that up on my website as soon as it's done. So we just saw some results in that video. In the paper, we actually investigated 15 different applications across 3 suspect devices. These are the results for the HTC One device. You can find the rest in the paper, but these are pretty representative of all of our findings. RetroScope recovered anywhere from 3 all the way up to a maximum of 11 screens for each app that we tested, with an average around 5 to 6 screens per app. It's worth pointing out that that maximum 11 screens actually came from the Chase banking application, and we were able to recover all of the screens of a banking transaction sending money from my account to someone else's. I should say this is not anything that the Chase banking app has done wrong, right? We are just telling the Chase bank app that Android needs it to redraw its screen now, and so the app is doing what it's programmed to do. Some other really interesting results, these are metrics from the re-execution piece. You can see that it takes a tremendous amount of re-execution to rebuild these screens. We found an average of over 40,000 bytecodes re-executed, and over 150 new Java objects and over 13,000 new C, C++ structures per screen. So this is all of that data that was previously lost that has to be rebuilt through this re-execution. So now one interesting case study that we found, these are deleted messages. And what you're looking at is the WeChat app, but we actually found this on a number of applications that we tested. What was happening here was the suspect was actively trying to delete the message that you see in screen -1. But of course, just because that message is no longer shown on the device's screen doesn't mean that it's totally gone. It was still in memory. And so RetroScope was able to re-render that deleted message as it looked when it was last on the screen. And even better, investigators get motive here. They know that the suspect was trying to delete this message because of screen -2 is the delete message options dropdown. And here's a really bizarre case study we found. RetroScope actually recovered a screen +1. That's a screen that even the suspect didn't get a chance to see. Now, the way this happened was the suspect was using WhatsApp and then put it in the background and put down the device. But before we could collect a memory image, they received a new message. And WhatsApp actually prepared a whole new screen with the new message on it that was ready for the next time the suspect was going to open that app. And so, of course, it was in memory, and RetroScope recovered it, and you could call it a screen +1, if you will. It's interesting because we only observed this in WhatsApp, so we assume this is some kind of WhatsApp-specific optimization to speed up bringing the app back from the background, but it's also a really cool result forensically. So of course, there's a lot of great related works in memory forensics. We started off this talk talking about guitar. I also just want to point out my paper Discrete because it's probably the most related work. Discrete also reflects this methodology of logic reuse, but for a totally different goal, and Discrete actually operates in a data structure specific fashion. So it's not at all automatic the way that RetroScope is. So in conclusion, we've developed RetroScope, which we really kind of believe is a new paradigm in memory forensics, being able to reconstruct all of that spatial temporal evidence that wasn't even available still in the memory image. And of course, RetroScope does this via the novel Interleaved re-execution engine that we saw. And you saw the evaluation results where RetroScope reconstructed these sequences of temporally ordered screens from 3 all the way up to 11 for a wide variety of privacy-sensitive applications. So with that, I thank you all very much, and I'm happy to take any questions.
Questions?
Really? Oh, okay.
Rabimbo, Rice University, awesome work. I just wanted to know, did you also notice this for only app specific, or like system apps, for example, will you be able to see the patterns of unlocking a phone like this?
Man, that's a really good question. So I don't know if the pattern draw that went to unlock the phone you're talking about, I don't know if that is in itself an application or if it's like a system service. If it is an application, I'm going to run back to the lab and test that. But we did test other system apps, things like the default MMS app that came with each of those 3 vendor vendor customized phones, and those worked all just the same. So yeah, it does work on system apps, but I didn't test the pattern. That's a great idea. Thank you.
Hey, Brandon. Great talk. This was really interesting. So what would a defense to this be if I want to hide my data from forensics?
Yeah, that's a great question. So defenses for this, well, let me do this. I actually have a backup slide for sort of the privacy implications of RetroScope, because that's actually, in fact, to be honest, when we ran RetroScope, even we were shocked at how much it recovered. So that kind of made us think, like, what's up with the privacy implications of this? So like I said before, these privacy-sensitive applications that we ran RetroScope on, they're not broken. RetroScope is not exploiting anything to do this recovery. The thing here is that most apps just assume that their memory is private. So there's little incentive nowadays to protect an application's own memory, right? Like, for instance, if you get a malware into your own memory, then you kind of assume all bets are off at that point. But what RetroScope is doing is it's just emulating the natural behavior of the Android framework. And so if you wanted to disrupt RetroScope, you would also kind of have to hinder the app's own ability to draw its screen, because we're just reusing those in-place redrawing routines. So you could think maybe one extreme way would be to add encryption logic into the app to encrypt that memory. But that probably wouldn't work because the decryption routines would have to also be in the drawing code so the app could show its own memory. And then you could come up with other approaches like zeroing out all of the data after you show a new screen. But then that's going to come with a lot of usability constraints because you'll have to get that data back the next time you want to show the screen, and you'll have to go to the network or to disk to do that. So you can think of a bunch of different ways of zeroing out memory more efficiently, but it's always going to come down to this privacy versus usability situation. And just in case you're worried, I don't know how much it comforts you, but normal citizens like you and I are protected from this kind of invasive forensics by pretty strict legal protocols. And this is things like you have to obtain a search warrant before you can do these kinds of invasive forensics. And there's also very strict chains of custody to use this stuff as evidence in court. So that's just something to consider. I don't know if it comforts you or not.
August Rudis, Google. So you mentioned zeroing out memory.
Yeah.
I'm wondering if something less involved, like just nulling out or just unlinking data structures on logout, would be sufficient to block RetroScope.
So if you explicitly went through and nulled out pointers, then it would make things more difficult for RetroScope. But then that's the same question of how is the app going to redraw that screen if it's already messed up the data structures that it was using?
Right, but if on logout.
On logout. Oh, okay. So that's a different question. Yeah, when you log out of an app, it probably should be cleaning up behind itself. But that goes to the first point where apps just assume that their memory is private. And so usually when you log out of an app, it's just setting a bit, right, to tell the app to ask you to log back in the next time you open it. And it just assumes its memory is private. I mean, when you log out, it'll lock, the encrypted databases and stuff, and it uses encrypted network traffic, but yeah, no one really has incentives yet to protect their own app's memory. Maybe this will start it.
I guess you'd think that they'd want to null out the pointers to trigger garbage collection, just as a sort of performance thing. Yeah. But anyway, thanks a lot. Awesome research.
Yeah, it's a great question. Thanks.
Hi, I've got a Patrick Hewlin, MIT Lincoln Lab. I've got a pretty technical question. Is there a reason you went the route of sort of kind of grafting this process from the target device out into a new Android emulator and then executing it there instead of just using the memory image as like a snapshot to begin running in like a new emulated Android process?
Yeah, so that's a good question, and actually one that I get frequently with the memory forensics work. It's actually surprisingly difficult to start re-executing a static memory image, because especially on Android, there is a ton of system services like open pipes. Like we just saw 2 talks about the binders and the intents and all these things that have to pair up very carefully with the runtime environment. So you could go the route that would be a ton of engineering to like re-piece back together all of those things. But the way that we did it was to use a good live environment as it was and then start grafting in from the memory image.
I see. Okay, thanks.
Yeah. Great question. Yeah.
Hi, I'm Moshe Kravchuk from Cisco. Great talk. Just a quick question. Could you elaborate on, did you grab the physical memory of the device, or it was application-only memory?
So that's a good question, because in a real forensics investigation, it depends on how you're grabbing the memory. RetroScope, the tool, is kind of at the end of that tool chain. So it only takes in a single application's virtual memory session. Okay. But if you're an investigator, to get there, then you take, all the way at the bottom, you could take a physical memory image. And then there's already tools that exist like volatility plugins that take in a physical memory image, split it into multiple virtual memory images, and then you could insert those to RetroScope, basically.
Thank you.
Yeah, no problem. Thanks.
All right, thank you very much.